Okay, so we're just taking a moment and going over one of the homework questions, or actually one of the review questions in the Chapter 2 skills quiz. And so this says we're going to want to find the value of the following expression for the given value of theta. And so we're given that theta is equal to 2 pi thirds. And so we want to go back in here, and wherever we see theta in our expression, we're going to rewrite that with 2 pi thirds. And so here we have tangent. I see theta there, so I'm just going to put a parentheses, go back in there in a second, and rewrite that with 2 pi thirds. And this is all over 4. So basically, I have this complex fraction, the tangent of, this is argument of what I'm taking of. So I'm just going to kind of rewrite this and simplify this before I figure out what that value is.
Sorry to barge in, but did you want us to write this for our notes as well?
No, you don't have to if you don't want to, but if you want them in your notes, you can put them in there.
Oh yeah, and prior to what the guy was talking about making PDF files, last semester there was a guy who introduced photos to PDF for iPhone users, and you can take photos on your phone, and then pretty much like they become PDF files, and then you can send it to like your Google Mail, and then once when you log in to Canvas and submit the homework, just go to like the Google files, and I think you should be able to upload it from there. That's how I did mine.
Awesome.
For iPhone users.
Okay, that sounds good. Thank you for sharing. I know there's lots and lots of ways to do it. I even Googled it and hundreds of things came up, but I know that maybe you guys have done it and know what's the best out there, and it's worked well for you in the past. So thanks for sharing. So you have 2 pi thirds, which is our numerator. Think of this as divided by 4. Another way of division with fractions, you're invert multiplying. So we can think of this as times 1/4, just to save some time. I can reduce this. I noticed that 2 in common in the numerator and denominator. And so I get that this is actually tangent of pi in the numerator and 6 in the denominator. Okay, so tangent of pi 6. I know that theta, or this value is pi 6. I know that this is in quadrant 1. And pi 6, if it helps you, rewrite it into degrees or think of it in degrees. Well, 6 goes into 180 30 times. So this is the same thing as 30 degrees. If for some reason you don't remember what tangent of 30 degrees is, or pi 6, and you just remember, hopefully you remember your sine and your cosine, remember all the trig functions can be written in terms of the sine and cosine. And so if it helps you, tangent, remember sine over cosine. So this is sine of pi 6 all over cosine of pi 6.
Is it root 3 over 3?
It is root 3 over 3, and you'll get that through this too. I know that once 30 degrees has the 3, so that's the root 3 over 3. It has more 3's in it. 60 degrees I know is just the root 3, but that's how my crazy mind kind of deals with memorizing it. Sine of pi 6, 30 degrees, this is 1/2, all over root 3 over 2. I have to invert multiply, so 1/2 times 2 over root 3. Gotta rationalize your denominator, 1 over root 3. Multiply by root 3 over 3, so we get root 3 over 3. Okay, so if you had fallen in a different quadrant, remember that's where you're going to use your reference angles, and it will give you either this value or the negative of the value that you would have gotten in the first quadrant, depending on which trig function you're using and which trig function, if it's positive or negative in that quadrant.
Thank you, Professor.
Yeah. Any other ones or things that you want to look at real quick?
No, that was it for me.
Okay. So we were just getting into limits. I believe. So let's just even open that up. So I'm teaching the calculus for business and social science majors and life science majors. So this semester, and so a lot of times we kind of overlap and the things, and sometimes I'll get confused on what I talked about. Did I already say that for this class? So please bear with me with that. And those videos will also be available. I'm putting those up onto YouTube, my YouTube channel. So if you ever want more problems to look at, again, that's another way to watch videos and see more examples. Okay, so sorry, just had to review what I was looking at. So we were looking at the graphs graphically. Actually, I think some of this, what I was doing was in office hours. I believe we stopped right here.
Yeah, we stopped on that, like, on the little straight grass, linear grass.
Okay, sorry about that. Let me just erase this really fast. I guess I could have done Okay, so before we even go back and jump into this problem, let's look at, ooh, I didn't realize there was a problem right there. Here's another example to look at maybe. Okay, so you're given a picture of a graph and it's asking you to find the limit and explain why they do not exist, or explain why it does not exist, excuse me. And so in order to show that a limit exists, you need to show that when you're coming into one side, the left-hand side on the graph, as you get closer and closer to that A value, you're getting to the same Y value as if you were approaching it on the other side of the X value. I don't know, remember how I said left or right? So here we have the limit, and we're looking at the limit as t approaches -2. And so locate -2 on the x-axis, which just happens to be actually on the x-axis here on the graph. And we want to look at first showing that the limit as x approaches -2 on the left-hand side. And so we denoted that with a negative looking like exponent up here of this function f of t. But notice as we come in on the left, even though it's an open circle there, meaning it is not actually a point on the graph, it's getting closer and closer to the y value of 0 there. And so the limit, as we're approaching x equals -2 on the left-hand side, the limit would go to 0. You want to do the same thing and look at the limit as x approaches -2, but now on the right-hand side of the graph. Technically, I'm putting x in here, and I just noticed my function is in terms of t, so I should really technically have t going to, not x going to. Just notice that. But as we come in on the right-hand side, notice you're also approaching the y value, getting closer and closer to a y value of 0. And in order for that limit to exist, they both had to go to the same value, even though that point is not, it's actually not a point on the graph. The limit as t approaches -2 of f of t is equal to 0. So part B, we're now looking at the limit as t approaches -1. So locate -1 on the x-axis or t-axis. We want to look at what's happening as we come in on the left-hand side. As we're getting closer and closer to x on the left-hand side, what's happening to the y value? Well, the y value you're getting closer and closer to, and actually hit there, is 1. Notice that's the same thing as if we were coming in on the right-hand side of t equals -1. So since you get the same value each way, then we can say that that limit exists, and the limit as t approaches -1 is -1. Okay, so notice we are going to have a problem for the second piece as we go in and looking at what's happening to the graph y values as t is approaching 0. And so notice there's a jump in the graph when t is equal to 0. And so we're going to get different values depending on what side we're coming in on. And so for part C, if we look at the limit as t is approaching 0 on the left, so coming in on the left, that's going to be this piece of the graph right here. And as we're getting closer and closer to t equals 0 on the left, this y value that we're getting closer and closer to is -1, even though it isn't that value there. And so now we want to see what's happening as we're coming in on the right-hand side of t equals 0. So coming in on the right, as we get closer and closer here, the y value that you're getting closer and closer to is +1, even though it's an open circle, meaning it's not actually a point on that graph, it just gets closer and closer to. And so since these are not the same, we can say then that the limit as x approaches, as t in our case approaches 0, of f of t does not exist. We did shorthand as d and e there. Okay, so why don't you guys just try it really quick? And you can put it in if you want the chat. What would you get if you were looking at the limit as t is going to -0.5? Sorry, I have to find this piece. What would you get as t is approaching -1/2? What is your y value going to? Or is it going to the same y value on the left and the right?
I think it's the same.
Okay, so it's the same, and what y value would you get back?
-1.
Yeah. So, right, so as you approach -1.5 here, or this is -1/2 in here. So go to where the graph is, locate the left of this side, which is, it's actually connected. And so as we get closer here, the y value is -1. And as we get closer here, our y value is also -1. And so the limit as t approaches -1/2 of f of t is also -1. Okay, so here is an example. Let's look at this example. Maybe, let me just erase it real quick. I was getting way ahead in office hours. Okay, so looking at the following, notice you have 3 graphs there. They almost look identical, right? Only difference is that in this first graph, you have an open circle. So let's just kind of think back really quick about graphing rational functions from college algebra or algebra. So remember when you're graphing rational functions, you want to see if there's any vertical asymptotes. And vertical asymptotes occur where your denominator equals 0, but not also your numerator. The other thing that you have to worry about when you're working with rational functions are values which set the denominator equals 0, because those are undefined and they're not in our domain. And so here, notice that this function f of x equals x squared minus 1 all over x minus 1. This is actually, we can factor the numerator. It's a difference of squares. We can factor this as x minus 1, x plus 1. All over the factor of x minus 1. And so here, I know I have a restriction, and my restriction is that x cannot be 1.
Was this the one we did yesterday?
Yeah, so this is a little review of the first piece, and then we'll look at the other two, because we ran out of time. So notice how we canceled this, and we got a reduced version of f of x, but we still had to have a stipulation here that x couldn't be 1. We found that there's going to be, because they both canceled, it was not an asymptote. It was actually just going to be an open circle on the graph. And so we talked that we could, let's look at just graphing f of x equals x plus 1. If you want to think of it, this is actually a linear line. It's in the form y equals mx plus b. My y-intercept is 1, right? My slope is 1. If I rise 1, go over 1. So I could graph this, right? But we said that it could not be 1. And I could figure out what that open circle is if I plugged back at 1 in here for x. So even though I know it's not 1, there's going to be an open circle there. So it's getting closer and closer to x equals 1 there. And this y value here, which ends up to be 2. So 1 plus 1, which is 2. Okay. So if you look at this, and we wanted to look at part A, and we wanted to look at the limit as x approaches positive 1 of x squared minus 1 all over x minus 1. Well, because we have this graph here, we can just look at it and we can say, okay, as your x value is getting closer and closer to 1 on the left, what is that y value that this is getting closer and closer to? Even though there's an open circle there, that y value you're going to get closer and closer to on the left and the right are the same. Right, so this is one that would be like 1.99999999999, and we're still getting so infinitesimally close to this 2, so we're going to say that that limit is 2. Same thing on the right, except that would be 1.01, 1.00001, so right, really close on this side. So basically part B is almost the same exact graph, right? Except instead of just having an open circle here, we have a point that's below it. So it's undefined at this point, 1, 2. But if I was looking at my function, in this case it's g of x instead of f of x, if I was looking at g of 1, it would tell me when x is not 1, or when x is 1, use this piece of my piecewise function. I get back a y value of 1. So that point does exist at x equals 1. It's just that we still have an open circle there. And so if you're looking at the limit as x is approaching 1 for g of x, again, you want to look at your graph. You want to find where 1 is, go up to where 1 is and where that graph is coming, and see what's happening as you're getting really, really close on the left and really, really close on the right. And again, even though there's an open circle there and there's a point defined below, graphically what's happening is your graph is really actually getting really, really close to 2 at that value. And so we would say that the limit as x approaches 1 of g of x is also 2. Okay, and that last case scenario is just that line, y equals x plus 1 with no restrictions in there and no open circles. And if we looked at the limit as x is approaching 1 of h of x, locate 1, come to the left, come to the right, see what y value the graph is getting closer and closer to when x is 1, which we get back to. Okay, so I think that this is a good representation to show that you could have limits going to the same value, and sometimes your limit doesn't even, or your function doesn't even exist at that value. It's not even in the domain. Sometimes it's not even a point where it's getting closer and closer to as you get closer to that x value. It might be way off and jump, but it's still the limit is going to go to that point, or it could even exist and the limit will exist. Okay. So let's look at the following and see which statement we think is true and which statement we think is false by looking at the graph. So this could maybe be a fun one to do just with a try it and you guys piping in on part A. So first part A, here we'll just do this one together and then I'll let you guys do the next one. So first part A, it says the limit as x approaches 0 of f of x exists. Or actually, I'll just have you guys chime in. So do you think that that's true? Say yes. If you think it's false, put no in the participant chat. So true or false? The limit as x approaches 0 exists. Got a 50-50 chance. Okay, well, anyone want to explain their answer or reasoning?
There's a jump in the graph.
Okay.
Well, like in the last graph, like you said, even though the points like from that specific like part on the y-axis would like go up, it's still approaching 0.
Exactly. So notice the second example up here where there was a jump in the graph. And if there's a significant jump where on the left-hand side, you're going to a different number than the right-hand side, and there's a jump like that, then it wouldn't exist. But in this case, this jump, this y value is getting still closer here on the left and the right, the same 2. And so same kind of principle with this over here. I hope you guys can't hear the vacuum going on in the background. If I was at my own house, I would probably be saying something, but anyways, I'd be yelling at kids. Actually, I shouldn't yell at kids if they're vacuuming, right? Okay, I can get sidetracked sometimes, sorry. So we have x is approaching 0. We're coming in on the left-hand side, so approach it on the left. You come in and you get 0. This is y is 0, and on the right, you're also getting 0. And so it does exist, it's true. And if we were to answer it, your answer would be 0. Okay, so what about, oops. hopefully you guys can now answer the second question. True or
Yeah.
false? Is the limit as x approaches 0 of f of x equal to 0?
True.
Okay. C, limit of x approaches 0 of f of x equals 1.
False.
False.
Right. If it's approaching one value and it exists at 0, it can't be approaching another value and still exist. So this would be false. Okay, what about the limit as x approaches 1? Is that equal to 1?
I mean, no.
I wouldn't think so.
I think it's true.
For the right side, yeah, but wait. Oh no, for the left side, yeah, but not the right side. Wait, what am I? I think I'm thinking wrong. Yeah, no limit.
Okay, so don't get mixed up between your x value and your y value. So first locate where x equals 1 is on the graph, which is right here. So when we're coming in on the left-hand side, so jump to the left and where the graph is on the left. What y value are you getting closer and closer to as you're approaching 1 on the left? What y value is that?
-1.
Yeah, so the result that is going to give you -1. Oops, I should put left. And if we look at the limit as x approaches 1 on the right-hand side, so jump to the graph on the right, so that would be this piece of my graph. So coming in on the right, what is your y value that you're getting closer and closer to?
0.
Right, 0. And in order for a limit to exist, as we approach that value, these have to be the exact same number. They're not the same number. And so we would say our limit as x approaches 1 doesn't exist. Okay. So maybe I answered some of the other stuff and going in here and explaining it. So limit as f of x approaches 1, we just said that that was false. So this would be true. No, actually it would never be true. The limit as x approaches 1 of f of x equals 0, is that true or false? Right, false. This would have been a true statement if it had told me coming in on the right-hand side, but it didn't. Okay, so the limit as x approaches c of f of x exists at a point c in -1, 1. What the heck? I'm not actually sure what they're asking. Let me see what they're saying. Exists for every point C. Oh, so this is not, this is actually, it's talking, I believe, as an interval. And so it's talking about between -1 and 1 that we're looking at in our graph here. The limit as x approaches C exist. So if you choose any number in here for your C value to look at for your limit, so let's say C was here. If I looked at the limit here as x approaches C, would that one exist?
Yeah.
Yeah, because the left and the right are coming to the same value here. And in this case, it would be -1/2. So it wants to know, though, if you choose any value that falls between this interval of x equals -1 and 1, could we say that that is a true statement?
Yeah.
Is there anywhere in there that you could choose a value for C which would make that false?
No.
Right, because basically here, It says because of the parentheses, it's saying we're not actually including that value. It'd be different if I was including that value. But basically, I can get really close to 1. So like 0.9, that's really close to 1. And I can come in on the left and the right of 0.9, and I would still be getting the same y value. And so in this case, this would be a true statement. Sorry, that kind of threw me off at first because it says point, and then that looks like a point, but it really isn't a point if they're talking about the interval.
So even if it did include the 0.1, wouldn't that still be a true statement because there's a point, but it's at 0?
No, it wouldn't work at 1 because like we looked up above here when we were looking at the limit as x approaches 1, notice that there's a jump in the graph there, a significant jump where your y values are going to be different depending on which side you're coming in on. And so when you're looking at the limit as x approaches 1, it doesn't exist because the left-hand side gives us -1, where the right-hand side gives us 0.
Okay.
But since they put that open circle there, I mean, we infinitesimally can get close to 1, and we would only be using this piece of the graph here, and it would be becoming the same y value. We just answered that. What about f of 0 equals 0? Is that a true statement? So looking at that graph, f of 0 equals 0.
That's false.
Yeah, so basically this is just a point, right? So it's asking this value in here that's inside the parentheses is your x value, and this is your y value. So this is asking, is 0, 0 a point on this graph?
Nope.
Nope, it's an open circle, so false. So f of 0 is 1. Is that correct?
Yes.
Yeah.
Yeah. When x is 0, we do have a point where y is 1. F of 1 is 0.
True.
Yep, solid. And then f of 1 is also -1.
False.
False because of this open circle here. And actually, if it had been 1, both of those were solid circles, we actually wouldn't have a function because it wouldn't pass that vertical line test. Okay, so we technically always just been looking at is graphs and being able to look at the graph, see if the left-hand side and the right-hand side coming into a particular x value was going to give you the same y value or approach the same y value it exists. We're also going to look at limits where we are just given that equation. And so a lot of times you don't want to go graph that equation. It might look really ugly. I might not even know how to graph it. And so having these limit rules can be helpful to find limits of functions that are kind of difficult. And so we have some rules in here and says, we're just going to let L, capital L and capital M, little c and little k, they're all real numbers. So we're not dealing right now with our complex number system. We're just dealing with real numbers. So it's telling me that if you have a limit as x is approaching some value of c of f of x and you get back L, so your graph here could be open circle or not, but here you're going to get back a value of L. And you look at your graph of g of x as x is approaching c, could be a function, g of x could look different. Who knows? And you get back m, then we can do the following. So basically, we can take a function, and if it's split up between pluses or minuses, we can rewrite it as the limit as the first function plus or minus the limit of the second function. And so being able to do this into simpler terms is helpful. So those are rule 1 and 2. 3 says that if you have some constant outside of your function, Instead of taking the limit with that constant in there, we can pull the constant out front of the limit, look at the limit of the function, and then multiply it through by k. And if we notice that we have a product in there, we can look at the limit of the first function times the limit of the second function, and that would give us back L times M. Same thing with a quotient. If you have a quotient, you can look at the limit of the numerator over the limit of the denominator, as long as that denominator doesn't go to 0. So this next one's kind of really helpful, power rule. And so if you have something raised to a huge power and you don't want to have to FOIL that all out and multiply it out and use the rule above, we can use this power rule where we can look at the limit of the inside and then just rewrite that inside of whatever that limit is to that power. And you can do the same thing with radicals. If n is even, we assume that f of x is greater than or equal to 0 for the interval containing c. They're just talking about our radical. Because we're talking about real numbers, we can't think of a square root of a negative number. It would give us back an imaginary number. And so to keep it informed with this theorem, we have to put that stipulation that if that's an even power, then whatever's underneath that function has to be bigger than or equal to 0. Okay, so let's use some of these rules to help us solve the following. And I kind of just this was from yesterday. So I just grabbed problems from the back of this section and I just kind of threw them in here before class. And let's just start really simple. And actually, before I jump into that, let me go over 2 rules with you before we do this. Let's say your function was a constant. Let's say f of x was just equal to some value k. Another way to write that, right, is y equals k. Remember, if you just had y equals a constant, that graph was just a horizontal line through that value of k. And so notice that anywhere you place c on the graph, but on the left-hand or right-hand side of that origin, when we look at the limit as x approaches c of a constant, what would you get back? So what is that y value you're getting back as you get closer and closer to this c on the left and the right?
Okay.
It's just your constant k. So basically, a rule says if you look at the limit as x approaches c of some constant k, this will just equal the constant k. The other one that these rules are going to help us stem with is looking at the graph f of x equals x. So let's just look at that real quick before I go over to that example. So if I look at the limit as x approaches any value, let's say c, of the function x. Well, if you graph that, if you want to plot points, or we know the y-intercept is 0 in the y equals mx plus b form. But basically, any x value I have, I'm going to get the same y value, right? I plug in 1 here, I get 1, 2, 2. -1, -1. Oops, that should be straight. So if I put c anywhere on here, and we look at the limit as x is approaching, and maybe we could say c was right here. C, what do you think that y value you're going to get back is? Sorry.
C.
What y value would you get back on that graph?
E.
I think I'm hearing my
180.
sound's not that great. C. Yeah, it would be C. Okay, so knowing those two things and those rules that we just discussed above, let's take this an example where we said, let's look at the limit as x approaches -3 of x squared minus 13. So one of the rules says that we can break this down as a difference of two limits. So the limit of the first term minus the limit of the second term. And so there was also this power rule, right? And it said, well, if you have something raised to a power, we can just look at the limit as x approaches -3 of x. After we take that limit, we're going to then raise it to the power of 2 minus, well, the limit of a constant is always just equal to that constant. And so this would just give me back 13. And so if I now, what I just showed you above, this would be the same thing as -3. So limit as x approaches a value c of x is just that c value, in this case, -3. We're going to square it from here, and let's bring down -13. So order of operations, -3 squared. And we get +9 minus 13, which gives us back -4. Okay, so right now I'm showing you a harder way of doing this. This is normally not this hard, because notice if we had just went into our original function and we plugged in that -3 wherever we saw an x, we would have gotten back -4, and it would have not been so hard to do. So I can limit as x approaches -3 of x squared minus 13. If I went in here, plugged in -3, squared it, minus 13, this equals 9 minus 13, which is -4. So much faster, so much easier. But the reason why we can do this like this is because of all of these rules above. And so for these polynomials, we can just go in and we can just substitute in the value wherever we have that value for x. Only things you're going to have to start worrying about is if you get 0 in the denominator, then it's not going to be defined. And then we're going to start getting into harder problems where we're going to get 0 over 0, or these indeterminate forms when we're taking these limits that actually don't tell us anything about the limit itself. But we're going to use a lot of algebra and things to manipulate them so that our limit will fall out. Okay, so let's do maybe one more. Actually, let's do the multiplication. It doesn't really matter. How about this one? So let's look at limit as x is approaching 2 of parentheses 2x plus 5 all over 11 minus x squared. Okay, so always with limits, really, if it's algebraic like this, the first thing you always want to try is just to plug in wherever you see an x. And if you get some value back, you're so happy, and then you're done.
Is that x squared or x cubed?
You're right, that's an x cubed, not a square. So looking at the limit as x is approaching 2 of 2x plus 5 in the numerator all over 11 minus x quantity cubed. So just go directly in, plug in those values. So we have 2 times, I see an x there, I'm going to put parentheses, go back and plug in 2 in a second. Plus 5 all over 11 minus, I see an x there, put parentheses, I'll go back and put in or 2 in a second, but we're going to cube that. Okay, order of operations, multiplication first. Numerator is like parentheses around it, denominator. So 2 times 2 is 4, 4 plus 5, that gives me 9 in the numerator. And then in the denominator, I have 11 minus 2 cubed. 2 cubed is 8. So 9 divided by 11 minus 8 is 3. So this would equal 3.
That seemed like it was simple.
It's not too bad. You know, next week we'll see it where we're going to have to start using tricks and things to manipulate things so that it does fall out nicely. Right now, it's just pretty much going in and plugging it in. 21, I mean, looks kind of scary at first, but I think it's actually not bad, right? You only see an h in this limit as h goes to 0 once in that expression. And so if we go back in here and we just replace h with 0, so this would equal 3 in my numerator. All over the square root, I have 3 times that h, and then plus 1 under the numerator, plus 1. And so simplifying that, I get this is equal to 3 in the numerator all over the square root of, well, underneath that radical, I have 3 times 0 plus 1, which is the square root of 1, which I know is also just 1. And so I'm left with 1 plus 1 in the denominator, which is 2. And so the limit here is just 3/2. Okay, so we did not finish, definitely did not finish 2.2 today, which I'm okay with because this is kind of the basis and kind of the foundation, these limits right here of a lot of what we're going to do in a lot of our following sections and chapters. And so I'd rather you guys get a really good foundation of what a limit is and how to find those. And then we can kind of hound the harder problems next week and get further. So I know I have that, I believe 2.2 is already due on Monday next week, but I'll move that and anything else that I said I was due on Monday. So just 2.1. I would get in though, and I would start 2.2 and try to do as much as I could. And that way you can see where you're struggling and maybe ask some questions next week. Let me stop the recording. And then I also have office hours right now in 10 minutes. I forgot, I haven't linked that Zoom meeting to the Canvas page. So I will get out of class in a couple of minutes and post that for everybody so they can get in if you want to come.